This is section 9.4 in your class notes on page 13, and we're going to be looking at several convergence tests over the next few sections. So in this section, we'll be looking at 4 of them, and so these 4 right here. Right, so this is on section 9.4. The divergence test, the integral test, the p-series test, and then the polynomial test. This is not in the textbook, but it's a very helpful and useful test. And then for comparison test, which is same thing as the direct comparison test, the limit comparison test, the ratio test, and then the root test, these 4 will be covered in section 9.5. And then finally, we'll be going over alternating series test and then the ratio test for absolute convergence. This will be covered in section 9.6. Okay, so let's take a look at the first test. So in general, we will use this notation of sigma of u of k as a general notation for a series. The starting index of k is equal to 0 or k is equal to 1 or some other value is irrelevant to the issue of convergence. And the reason is that you're going out to infinity, so it doesn't really matter where you begin. The kth term in an infinite series of the sigma of u of k is called the general term of the series. So the first test that we're going to look at is what we call as the divergence test. And this basically is a disqualifying test. So the theorem, it states this way. If the limit of the kth term as k goes to positive infinity does not equal 0, then the series diverges. However, the second part of it is, if the limit of u of k as k goes to positive infinity equals 0, then the series may either converge or diverge, and sometimes they just use that word inconclusive. Okay, so this is a good example of this is when you apply to colleges. If you do not apply to a college, there's no way that you're going to get into that college. However, if you apply, it doesn't mean that you get in. So if you do not apply, which means that u of k does not equal 0, then you don't get in, which means that it diverges. But if you do apply, which is u of k equaling 0, then you may or may not get in. So maybe you could use the college admissions example as a reference to that. Okay, so if the series does not converge to 0, then the series diverges. If the sequence does not converge to 0, then the series diverges. If the sequence converges to 0, then the series may converge or it may diverge. Further testing is required, and here are 2 examples. So the first example is 1/2 plus 1 over 2 squared plus 1 over 2 cubed and so on. So this is a geometric series with the common ratio being a half. So we know that the sequence, it converges to 0, meaning that the kth term, if I took k out to infinity, this would be 1 over a large number, which goes to 0. And also the series converges. So a sequence converges and the series converges. So the sequence and the series both converge. In this next one, you have 1 plus 1/2 plus 1/3 plus all the way to 1 over k. So if you look at the sequence, it converges to 0. If I take 1 over k and let k go out to infinity, then it's 1 over a large number, which goes out to 0. But this is a harmonic series, and the series, it diverges. Right? So the series, it diverges, but the sequence, it converges. So you need to make a distinction between those 2 things. All right, the theorem on this is if the series converges, then the limit of the kth term as k goes to infinity is equal to 0. So that would be a true statement. The converse is a false statement. So if you switch the hypothesis and the conclusion, it's if the limit of the kth term as k goes to infinity equals 0, then the series converges. That is a false statement. And so the case that is false on this would be with the harmonic series. Okay, so this is on page 14, and here's an example. Show that this series diverges. So I'm going to look at the kth term. So take the limit of k over k plus 1 as k goes to infinity. So you'll be doing it just like you did with your sequence in section 9.1. Since it does not equal 0, it equals 1, then the series diverges by the divergent test, and then you're done with the problem. Okay, please read over the properties of infinite series. It's pretty much what you think that it would be. And so you have the sum is equal to sum of the series separately. The difference is equal to the difference of them separately. If you have a constant, you can pull it out in front of the series. And then your series is divergence and convergence is unaffected by whatever number it starts off with. So if you start off with k is equal to 1 and then go out to infinity versus k is equal to any number, it could be even 50 if you wanted it to be, going out to infinity. If the previous one converges, it converges. If it diverges, then it diverges. All right, so for this next one, I'm just going to be using the theorem about subtraction. So I can take each of these separately, right? So for this one here, I have the limit or the summation of k is equal to 1 out to infinity of 3 over 4 to the k power. And so if I work this out, this is a geometric series. And so working out the common ratio, I get it to be 1/4. And then the sum of it is the first term over 1 minus the common ratio. So I get the sum to be 1. And then the second part of that is 2 over 5 to the k minus 1. So I write out that series and I get the common ratio to be 1/5. And so this is going to be sum is the first term, which is 2 over 1 minus r, so 1/5. So the answer there comes out to 5/2. So then the overall sum would just be the first sum minus the second sum. And so that comes out to a negative 3/2. Okay, so for the next one here, determine whether the following series converges or diverges. And I'll pull out the 5 in front of the sum, and I get 1 over k. I know that 1 over k is a harmonic, so a constant times a divergent harmonic series also diverges. And then for this one, I'm starting at k is equal to 10. So then I have k is equal to 10, and so just because I start at 10, it doesn't really change the convergence or divergence. This is, again, still a harmonic, so then it diverges, and that would be by the harmonic series. Okay, the next test I want to look at is called the integral test. And we see the expression of 1 over k squared, and it relates to 1 over x squared. So see how this is written. In place of the sigma, I'm using the integral. The lower bound of k is equal to 1 becomes the lower bound of 1, and then the infinity up on top is the upper bound. And then I'm going to be taking the integral. So the following theorem shows that there's a relationship between the convergence of the series and the integral, and it's stated this way. So this is called the integral test. If you have u of k as a series with positive terms, and if f is a function that is decreasing and continuous. Okay, so those two are important. It's got to be decreasing and it's continuous on the interval of a to positive infinity, such that u of k is f of k for all k greater than or equal to a, then you can rewrite it this way. Right, so the kth term, you can write it out as f of x, and then the lower bound becomes whatever your lower bound in the sigma is, and then the upper bound is going to be infinity. So if this converges, and we know this from chapter 7, how to deal with these problems, then that means that the series converges. Right, so if this converges, this converges. If this diverges, then this diverges. So if the integral diverges, then the series diverges. If the integral converges, then the series converges. Okay, so let's look at this example. And I'm going to use the example of the harmonic. And so I'm rewriting this as 1 over k. So it is integral of 1 over x dx, and then 1 out to infinity. And that is going to equal, I'm going to cover this bottom one up here. So I take the integral of 1 over x and then evaluate that, and I get the answer to be infinity, which means that it diverges. So if the integral diverges, then that means that the series diverges. Okay, I'd like you to try the next one on your own and then come back to the video. Okay, here's the solution. So I rewrite it as the integral of 1 over x squared going from a 1 to infinity, and then I take the improper integral and evaluate it, and then take the limit, and then I end up with the limit of 1 over x as b goes to infinity from b to 1, evaluate that, and I get 1 minus the limit of 1 over b as b goes to infinity. So b 1 over b as b goes to infinity would be 0. So it's 1. So this converges, which means that the series also converges. So since the integral converges, that means that the series converges.